everyone, and welcome to this module on Introduction to Continuum Mechanics. So in this module, we are going to discuss the rate of heat flow as well as energy equation, or the first law of thermodynamics, and entropy inequality, the second law of thermodynamics. So far we discussed three principal equations: conservation of mass, the linear momentum, and the moment of momentum. The fourth and the fifth equations are entropy equation and energy equation and entropy inequality. So finally, we end up with five principal equations. All right, so let's get started by the rate of heat flow. All right, so if you remember from the principle of linear momentum, or the equation of motion, we already had kind of an element in here where we had our right here. So we had x1, x2, and x3. So it's a right-handed coordinate, right-handed basis. And here we had this kind of element where we applied the tractions on its surface, and it was also exposed to the body force. So now, analogous to traction, we here define the heat flow. And so here traction was basically the force per unit area. And now we are going to define something analogous to T. So it is Q, and it is basically the heat flow per area. This is what I already mentioned up until now. And this Q is basically heat flow by area by conduction. And now we are going to find the net heat flow by conduction, because this is a vector, so we have a contribution on all these on all sides of this element. All right, so let me change the color, and right here, that on this side of the element we have QE1, let's say x1 plus dx1, x2, and x3. And here I can show this, this is a subscript in here. And then on this side we have minus, QE1 minus x1, then we have x2, x3. So basically this is dx1, this is dx3, this is dx2, and this is dx3. And the book basically used the minus sign if the heat flow actually enters this element. So if we have a room, we are in a room, for example. Let's suppose this is your room, and your room has a door like this. So if we have a heat, or let's say wind, for example. So if we have wind entering your room with Q, the vector Q, so only the wind that is normal to the surface can enter your room. This is Q dot, if this is, if let's say this is n, this is normal to this surface in here. So we have q dot n. And this is nothing but the projection of q on n, q dot n. So we also have this element of q, which they go over the boundary. So they do not enter this door. That's why we only include q dot n values in our calculations. So with this in mind, we simply write, so we have QE1, which is simply Q dot E1. It's because the normal to this surface is E1, and this is X1 plus, or let me just write this in this format, X1 dx1, then we have X2, then we have X3. So on this surface, we found the heat flow per unit area times E1, so it's Q dot N. And since it is entering our element, so the book used a minus sign in here, we have a minus sign in here. Then we have, again, a contribution from this side. So here again, we have a door, for example, and we have a Q in here. So this Q, again, is can be decomposed into two vectors here. So these ones are tangent to the door or the boundary that we have in here, to the wall or the boundary that we have in here, and they do not enter our room. The only ones that enter our room are these normal ones. This is Q dot N. Therefore, we'll have minus Q, and here we have the normal is minus E1, right? So we have a minus in here. So a minus contribution and a minus here, so it becomes positive. So this becomes E1 again. Remove this head here. Then we have X1, X2, and then X3. So, and we also, since these are per unit area, so we have to time all. We have to times, we have to find the product of this with the area in here, this area in here, which is dx2 dx3. So if you remember, this can be written as, this is the definition of the gradient, so it can be written as the partial derivative of q with respect to x1 dot e1 q dot e1 with respect to x1 dx1. Next we have dx2 and dx3. This can be written as this. So if I expand this, I have minus partial derivative of q with respect to x1 dot e1 dx, or let me just get rid of this dx1 and dx2 and 3. So I will write this down in here. So dx1, dx2, dx3, and I only open this one. So I I expand this one. So we have q. So we have minus q dot partial derivative of e1 with respect to x1, which is basically 0. This is constant. So finally, we end up with, right, with minus partial derivative of q1 with respect to x1. So because here we have q is a vector and dot e1, so this only gives values when we have q1, otherwise it becomes 0. So we have q1, then we have dx1, dx2, and then dx3. So if I do the same for others in here, so for example, if I do this for in here, for this size in here, so I'm gonna have this is 2, so QE2, x1, x2 plus dx2, then x3, and then we have QE2 minus x1, x2, and x3. Then for this one, I have the same equations. However, this one basically changes to, since the normal here is x e2, so I have e2, then this is x2 plus dx2, this is e2, and this becomes basically, now the area is dx3, dx1. So this becomes dx1, here we have e2, and then we have dx2, dx1, then we have e2, and this is of course 2, and then we have 2, this becomes 2, and finally we have partial derivative of q, so 1, 2, 3 dot e2, where this gives only the values for q is equal to q, where we have only q2, so it becomes this. Next, if we have, for instance, on this side, we're going to have q e3. Let me write it. Q e3. So it's x1, x2, and then we have x3 plus dx3. And then on this side, we're going to have QE3 minus x1, x2, and x3. Therefore, we finally get, I'm not going to repeat everything in here, or maybe it's a good idea to repeat everything for the sake of consistency and completeness. So here we have E3, then we have this x2 in here, then we have x3 plus dx3, we have e3 in here, then we have this is applied on dx1, dx2 on this surface, dx1, dx2, then this is x3, this is of course e3, and this is dx1, this is dx3, and this is dx2. So this is e3, this is 3, this is also 3, and this is also 3. So this becomes q1, q2, and q3 dot e3. So we only have q3, and then this is x3. So here, if we sum all of these values in here, so 1, 2, and 3, so 1 plus 2 plus 3. Basically, we call this QV, and it is equal to the minus of partial derivative of q1 with respect to x1 plus partial derivative of q2 to x3 plus partial derivative of q3 with respect to, sorry, this is 2, x3. Then we have dx1, dx2, and dx3, which is basically dv, the volume of the element, and this is simply equal to the divergence. It's minus qi xi dv, or minus delta v dv, or divergence of, oh sorry, this is divergence of q dv. All right, and we call this qc as the net heat flow by conduction, because this qc is a contribution of 3 terms in here. All right, so now let's get to example 4.14.1, where we have the Fourier heat conduction law. Where it states Q is minus kappa del theta, where we have theta as a temperature and kappa as a coefficient of thermal conductivity. So basically, we can use this Q in order to characterize the heat conduction. As you see here, this law uses the gradient of theta, but one thing which is evident here is the neglected effect of the velocity. So it's like when you have a wire and you hit it from here, for example, this hit can be, let's say, felt by the material which is in this point. So it says that the velocity of heat conduction is basically infinite, which is not true in reality. However, this can be accepted with, with certain assumptions. But overall, this is the Fourier heat conduction law. And so we're going to find out basically the QC in here. So QC is basically equal to the minus divergence of Q. So dV. So the divergence of V is basically, sorry, the divergence of Q is basically, it's the partial derivative of Q1 with respect to X1. So it is the partial derivative of kappa delta theta with respect to X1. And this delta theta itself, let me just write it down in here. So then we have minus kappa delta theta. It's a derivative, it's partial derivative with respect to x2, plus the partial derivative of minus kappa del theta with respect to x3. And del theta itself is the gradient definition. So this can be written as minus kappa partial derivative of theta with respect to x1 plus, here we have minus kappa partial derivative of theta with respect to x2 plus partial derivative of minus kappa partial derivative of theta with respect to x3. So this can be written as, if we assume that kappa is a constant value, so we can take this out and write this as second partial derivative of theta with respect to x1 plus second partial derivative of theta with respect to x2 plus second partial derivative of theta with respect to x3. And this is nothing but the Laplacian. So del 2 theta. So if this is equal to 0 for a steady state problem, so we have two problems. We have the steady state, so where there's no change in del theta, so therefore del 2 theta becomes 0. This k is a constant value, so it can be removed. So it becomes a Laplace equation. If it is equal to a constant value, for example, f, it becomes a Poisson's equation. So here we have 0, and then we have the transient problems where theta actually is changing and it reaches a certain value after a certain time. So we can't make this kind of assumption in this kind of problems like unlike the steady state. All right. So the next topic is the first law of thermodynamic or entropy equation. Entropy. Sorry, it's energy equation. So let us define some terminology here. So let's say U is the internal energy. We already know this. And Ke is the kinetic energy. We also define this. So here we have Qc, which was the net rate of heat flow. So we also put an inflow because it is entering the element, it is entering the boundary. So it is entering from the boundary by conduction. And we have P, which is the rate of the work done, or the power by, if you remember, we had body forces, and we also have a contribution from surface forces. And let's say that in your, for example, in the room that we also have a furnace, for example, and this furnace is basically generating some kind of heat inside the element or inside the volume that we have in here. So this acts like a heat source, like, for example, radiation, as the book said. This could be a way of generating heat inside the room or inside the volume that we have. So we also have to write another term here, Qs, and we call this the rate of heat input. The rate of heat input. So Basically, the first law of thermodynamics or the energy equation says d dt of the summation of u and ke. So it says that the rate of increase of the internal, this is u, the internal energy, and the kinetic energy of a particle is equal to the power or or the work done by external forces, which includes both the body forces as well as the surface forces, plus the rate of heat in flow by conduction from the boundary conditions, of course, plus the rate of heat generated inside of the volume. So if I want to write this down here, write it in this way. So the rate, because this is the rate of increase of, we have internal and kinetic energy of a particle is equal to the net sum of the rate of work done or the power by external forces, or let's say the body forces, the surface forces, including body force plus surface forces, of course, on the boundary. It's better to write it this way. And so we have QC, rate of heat inflow, again from the boundary, and the rate of heat input. Sorry, rate of heat, let's say generated, generated inside the volume or the particle or throughout the volume, as book already said. So if I just move this bit, here we have the energy equation. So this is the rate or the material derivative, remember here. And here we have the summation of internal and kinetic energy equal to the work done by the external forces, including both surface and body forces, heat inflow from the boundaries, and then heat generated inside the volume. So we have this equation here, and we are going to basically derive this in the in its differential form. So to derive the energy equation in let's say differential form, we know that basically P is equal to the rate of, so we have kinetic energy plus Tij partial derivative of Vi with respect to xj dv. So if you remember, this was del v was the gradient of the velocity, the velocity gradient, if I'm not mistaken. So we have this in here, and we also have qc from here. It was equal to minus the divergence of qv. So it is equal to minus, let's say, divergence was xi, then we have dv. So if we substitute this in here, then we're gonna have d. So this is 4 and this is 5 in energy equation. So 4 and 5 in equation. So we have du dt plus d kinetic energy dt, because we can simply differentiate over this plus over this, is equal to, then we have d kinetic energy dt, this is p, plus t ij partial derivative of v I xj dv minus, then we have partial derivative of qi xi dv. Then we have qs, and we can write qs as this. All right, so now we can cancel out this in here. Next, we define u as the derivative, as the internal energy. So capital U was the internal energy, and we define U as the internal energy per unit mass. So basically, du is equal to du divided by dm, for example. So then I have du dt. So du dt becomes d dt. So we have u, so we have u dm because we have small element in here. So this becomes d. Sorry, I guess that I have to remove this m in here. So we have d u dm, so I can write this as d. So I can change this dm to rho dv. So I have d dt of u rho dv. So I can write this as du dt rho dv plus u d rho dv dt, which is equal to 0 due to the conservation of mass. So let me write it in here. So we have then we have du, rho dv du dt is equal to tij. So I can write maybe star, or let's write this as 5, this is 6. So 6 becomes tij partial derivative of vi xj dv minus partial derivative of qi xi dv. And here I write qs, like qi. I can write qs as capital Qs as qs applied to, let's say, to the material, to hold the material, or rho dv here. So I define qs as small qs rho dv. So since dv is not equal to 0, I can get rid of this. So finally I have rho du dt is equal to, then I have t ij partial derivative of vi with respect to xj minus partial derivative of qi with respect to xi plus rho qs. And we know that this tij is basically rho, rho du dt is equal to, this is the trace of td minus, and this is the divergence of q plus rho qs. And this is basically, oops, the energy equation in its differential uh, format. So this is uh, so for example, suppose you're solving an elasticity problem. So in an elasticity problem, you basically have no contribution from, let's say, Q and QS because there's no heat. So these terms are basically zero. So you can solve this equation for only this portion in here. But suppose you're solving a thermoelasticity problem. So you have to also include these terms in here. And the whole equation should be solved. All right, and here you have to define, let me just change color. So you have to find T, you have to find, let's say, Q, and you have to also find a U. So you can find this T's, Q's, and U from experiment, and you can just plug them into this equation and solve this in reality. Here U is a material characteristic, and it can it depends on the deformation as well as uh, temperature. So you can simply find this from the tests on experimental mechanics and just plug them into this equation, solve this. All right. So next we have the entropy inequality. So far, we discussed four principal equations: conservation of mass, linear momentum, momentum, and this one, energy equation, or the first law of thermodynamics. And there were like all equations, they were equal to, they were not, they were basically equality. But this one in here, the fifth principal equation, or the entropy inequality, uh, this one is is an inequality. So we defined eta as a function of x and t. So it's a function of uh, coordinate and also time. We define this as entropy per mass. So if we want to find entropy, for example, so you have eta, it's a function of x and t dm, or this becomes rho dv. So this becomes entropy. So we basically, if we take the material derivative of entropy, so eta rho dv dt, we can write this as dE theta dt rho dv plus eta d rho dv dt. This one becomes zero due to the conservation of mass. So we finally have rho dv d eta dt. And we call this the rate of increase of entropy. So basically, the entropy inequality states that this rate, this rho dv d eta dt is at least equal. So it is large, it's bigger and equal than the divergence of q divided by theta dv plus rho qs divided by theta dv. And if we drop these dv's from here, so we're going to end up with the second law of thermodynamic or entropy inequality. So what it states, so basically it says that here where we have the rate of increase of entropy in a particle is at least equal or bigger than this summation here. So here we have the entropy due to the inflow across the boundary. It's better to write it the surface boundary. And then we also have a contribution from the heat generated inside. So also the entropy through out or inside, let's say the entropy due to the heat, or maybe entropy inside the volume generated inside the volume or inside a particle. So this is basically on the boundary, and this term is basically inside. So it says that if you have an element like this, and you have some heat inflow from the boundaries and also some inside it, so it will contribute to increasing to its entropy, and the entropy of the whole system is at least equal to the summation of these entropies, but it could be also bigger than this summation of the entropy inflow across the boundary and the entropy generated inside the volume. All right, so now let's get to example 4.16.1. So basically this example uses the Fourier heat conduction. So we have Q equal to minus kappa delta theta, where we have a bar in here. So this bar in here starts from here. So this is x. So at x equal to 0, x1 equal to 0, theta, we have theta 1. And at x2 equal to L, we have theta 2 as the temperature. And the length is, of course, L. So it asks us to solve for the temperature distribution. So for temperature distribution, we have the partial derivative of Qi with respect to Xi, because here we only have a contribution from the heat inflow. So there is no Qs, so the term is 0. This is equal to the partial derivative of, let's say, minus kappa, partial derivative, del theta. So this is basically, let me just put down in here. This is equal to, so if you remember, we already calculated this in here. So it is this value in here. So if I take out this, just paste it in here. So from example, it was example 4.14.1. So from example 4.14.1, we have this equation in here, and since our problem is one-dimensional, these are 0. So we finally have minus kappa partial derivative of theta, second partial derivative of theta with respect to x1. And since we have a steady state problem, so assuming that we have a steady state problem, so this is equal to 0. So if we solve this problem, this equation here, second partial derivative of theta with respect to x1 is equal to 0. Therefore, we have the first partial derivative equal to c1. So it's constant value. Then theta basically becomes c1x plus c2. So we have to find c1 and c2 from the boundary conditions. So at x equal to 0, we have theta 1. So theta is equal to theta 1. Therefore, theta 1 is equal to c2. And at x equal to L, theta is equal to theta 2. Therefore, we have theta 2 equal to, this is c1L plus c2. And c2 is nothing but theta 1. Therefore, c1 is theta 2 minus theta 1 divided by L. Therefore, we have theta equal to theta 2 minus theta 1 divided by L, x plus theta 1. In the next section, we're going to prove that k is basically bigger or equal to 0. So for this, we're going to start from the differential form of the entropy inequality. So here we start from here. And as I already mentioned, this term is 0 because we have no heat generated inside the volume, and we assume that entropy is not changing with time. So its rate is equal to 0. This is the assumption that we make solving this equation. Therefore, we finally end up with 0 bigger or equal to minus the divergence of q theta. And this q is basically the minus divergence of minus k delta theta, where this is equal to, so I have minus minus, so it becomes plus, k is constant, I take it out. So here we have the divergence, so it is the partial derivative of this whole theta, and then this is equal to the partial derivative of xi, and del theta itself, okay, I have to made a mistake in here, so this is theta, and this is again the partial derivative, so I have the partial derivative of theta with respect to xi. So 0 is bigger or equal than kappa. Then we have kappa. Sorry, this is the partial derivative. So we have the partial derivative of the first one. So it is the partial derivative of 1 over theta with respect to xi. Partial derivative of theta xi plus so we have 1 over theta, we have second partial derivative of theta with respect to xi here. And since we have one-dimensional problem, so we only accept I is only equal to 1. So it is the partial derivative of 1 over theta. If we expand this, it becomes minus partial derivative of theta. Oh, sorry, it becomes 1 over theta 2, partial derivative of theta with respect to x1. And we also have partial derivative of theta with respect to x1 plus 1 over theta. Second partial derivative of theta with respect to x1. So since we assumed a steady state problem, so this becomes 0, steady state. This is the assumption that we made. Therefore, we have 0 greater or equal than minus kappa divided by theta squared, and then we have this partial derivative of theta x1, and then again we have this partial derivative of theta x1, so it becomes squared. So this is positive, and 0 is greater than this. So for this, k should be greater or equal to 0. All right, so now we're going to explain the entropy inequality. So we're not going to bring a new principle equation. We're going to again use the entropy inequality, but in another form. We're going to express this in the form of Helmholtz energy function. So basically, we have entropy inequality in terms of Helmholtz potential function or energy function. So the philosophy behind this Helmholtz energy function is, when you have, so I separate this as background maybe. So you can increase the internal energy inside a volume with a contribution from heat and also contribution from the external work. And this heat can be written as theta, basically d eta, so entropy times theta. And here we have dw, which is tij d, let's say eij, let's say, or let me write it as, I don't know, maybe let's write it as epsilon ij, because I'm not going to use ee star or small e to just uh, confuse you if I use a special case of strain tensor in here or deformation tensor in here. So let's just call it epsilon. It's the strain. So here we have the stress and here we have the strain. So based on this, you can see that u is basically a function of eta and epsilon, of eta and epsilon, which is a function of, let's say, eta and epsilon ij. And this eta is a bit difficult to measure in the lab and by the testing. Therefore, we are using other functions like Helmholtz energy function in here to get rid of the effect of eta. So we use basically an intermediate function uh, to uh, to actually calculate the to find the internal energy. So Helmholtz energy function, in Helmholtz energy function, we have U equal to, so Helmholtz energy function. So this energy function is going to replace U. So we define A is equal to U minus theta eta. Therefore, I can write U as A plus theta eta. So if I take the derivative of this, so it becomes dA plus, here we have theta, sorry, it's d theta eta plus theta d eta. So if, and also I have du is from here, so it's theta d eta plus tij d epsilon ij. So now, if I have these two and I equal these two, I can get rid of theta de theta. Then we have dA plus d theta eta is equal to tij d epsilon ij, or dA, the Helmholtz energy function, is equal to tij d epsilon ij minus d theta n. Now you can see that A is a function of epsilon ij and theta. So it becomes a function of deformation and temperature. So we basically remove the effect of entropy, dE theta, which was previously existed in U. And remember, this epsilon here is, you know, a representation of all the deformations. All right, so now with this background, I'm going to also separate this, the rest of the equations in here. So we're going to find the entropy inequality in terms of the Helmholtz energy function. All right, so previously we ended up with this equation here. the inequality equation, the entropy inequality equation. And now we're going to get rid of these the uh, epsilon d eta dt. So for this, we're going to use the first equation here. So the energy equation in differential format. So we copy this. So to remove the eta dt, we would like to use to replace, basically, to replace u in energy equation with the Helmholtz energy function. So we replace u in here from here. So we have a plus theta eta. So we have a plus theta eta dt. So if we take the derivative of this, we will have partial derivative of dA dt plus rho. Then we have the second term in here. So we take the material derivative of theta eta. So it is the first derivative of the material derivative of the first term in here. So we have theta d theta dt eta plus rho. Then we have theta plus the material derivative of the theta dt. All right. So this is basically equal to the trace. So copy, paste this in here. So this is equal to the trace of td, or is equal to tij partial derivative of vi xj minus, then we have divergence of q, which is partial derivative of qi with respect to xi, plus rho, then we have qs. So here I guess that I made a mistake, because here we had this, and in the inequality we had rho d theta d theta, or let me just copy, paste in here. So no, it's fine. Okay, so now I'm going to take out this d theta. Yes, I'm going to take out this, let's say, term in here. So if I multiply here both by theta, then I'm gonna get theta here, theta in here, and also this theta will be removed. So maybe if I write this in here, so this will be cancel out this one. And if I push this a bit down, so I'm gonna get rho theta d theta dt is equal to t, or minus, let's write minus rho dA dt plus rho d theta dt eta. So I'm simply taking this to this side of the equation. Plus tij partial derivative of vi with respect to xj, vi minus partial derivative of qi with respect to xi plus rho qs. And I push this a bit down. So now I plug this into this in here. So then we have this equation. Paste this in here. And then I have copy, paste this in here. So I can get rid of this theta here. And this is, of course, minus theta. Because this is not theta minus. So I take this in here. So from here, we can see that we can get rid of, sorry, this is theta. So we can get rid of this and this. And we have theta in here. So let me just push this a bit to the right. This is theta, all right. So then we have this in here, and then we have theta divergence of, this is the minus, sorry. So minus. So this theta, so if I just write this with another color, just to recognize this with another color. So theta divergence of q theta, it can be written as theta partial derivative of q divided by theta with respect to xi, which is equal to theta. So then I'm gonna have 1 over theta partial derivative of q I with respect to xi minus theta 1 divided by theta squared. Then I have q here. Then I have partial derivative of sorry, this is qi also. I might have forgot this. All right, so we have the derivative of qi. So this is correct. So this cancels out this one minus theta. And this is the partial derivative of theta with respect to xi. So this cancels out this, which becomes finally partial derivative of qi with respect to xi minus qi divided by theta partial derivative of theta with respect to xi. So let's plug in this into, it was, I guess, the last equation was 6. Let me find what was, this is 4. So we can write this as, for example, 6 or 7. So this is 6. And this is 7. So if I put 7 in 6, so what we get is this portion. So if I copy, paste this, or maybe push this down, then we have the minus of this, so this equal minus qi xi plus qi theta partial derivative of theta xi. So this also cancels out this one. Then finally we get this in here, and I take this to this side, to the left side. So I have qi theta derivative of theta with respect to xi is bigger or equal to 0. And that's it. This is the entropy inequality in terms of Helmholtz energy function. So you can see here that the effect of d theta is basically removed, and finally what we have is just the variation of just a, and we have theta. So next is the example for 17.1. Oops. So this is example for 17.1. So basically in this example, we have the linear thermoelasticity, and so we assume that A is a function of EIJ, the small strain tensor, infinitesimal strain tensor, and theta, just the temperature, like the one that I already mentioned here. So here we have the general deformation epsilon ij, and then theta. Here we only have, instead of epsilon ij, which was the representation of all the deformation, we have the infinitesimal strain tensor. So now we're going to derive the relation between the stress tensor and the Helmholtz energy function. So for these, we may start from this term in here. So we have dA over dt, which is equal to d. Since a is a function of eij d theta, I can use the chain rule. So I can use, dA deij, then deij dt. And since here we have dA is a function of both eij and theta, we have to use partial derivative instead, plus partial derivative of a with respect to theta d theta dt. So now we're going to find deij dt. So if you recall, we had half of, or let's write this like this. So we had half of partial derivative of ui for the infinitesimal strain tensor xj plus partial derivative of uj with respect to xi. So it was equal to, if I can take out this half in here, so then I have dt of partial derivative of ui with respect to xj plus dt of partial derivative of uj with respect to xi. This is equal to half of, so here we have a partial derivative and we have material derivative. So both are basically the derivative. So we can swap them. So we can first do the material derivative and then the partial derivative, either or we can do the partial derivative and the material derivative. I prefer to do the material derivative first because then it gives us the velocity. So it becomes the partial derivative of xj. Then here we have the d of ui dt plus, because this becomes again vi, and then we have the partial derivative of xi duj dt, then this becomes vj. So this is basically equal to half of partial derivative of vi xj plus partial derivative of vj xi. And since we are assuming linear elastic or linear elasticity and infinitesimal strains, deformation, so we can say that uh, the material derivative and the spatial derivative are equal to each other. So we can, oops, so we can say that this is approximately equal to partial derivative of vi with respect to xj plus partial derivative of vj with respect to xi, which is basically the del v plus del v transpose. So half of del v plus del v transpose, which is basically dij, the symmetric part of the velocity gradient. So now we found that the material derivative of eij is equal to dij. So we can just plug it into this equation. So next we can write minus rho. We had the partial derivative, let's say, of a with respect to eij. Then we had the material derivative of eij, which is dij. Then we had the plus rho d theta dt eta. Then we had plus tij plus tij dij. So this is dij minus qi divided by theta, partial derivative of theta with respect to xi greater or equal to 0. So now we can take these two terms together, and I guess that I have, yeah, we also have a contribution from here that I missed. So partial derivative of a with respect to theta, then d theta dt. Right, and then we have d theta dt, this term, and this term goes by itself. So here we have minus rho, partial derivative of a with respect to eij plus tij dij. Then we have plus, then we have minus, and okay, so I can take this as minus rho partial derivative of a with respect to theta plus rho eta d theta dt minus qi theta partial derivative. All right, so now to solve this, we can first keep these two parameters constant and then change di. Therefore, these two become 0, and then we have, so in case d theta dt is equal to 0 and partial derivative of theta with respect to xi is 0. Then we have minus rho partial derivative of a with respect to eij plus tij dij is equal to 0. So for this to be 0, this can be 0 because we are basically changing this. So then tij is equal to rho partial derivative of a with respect to eij. So it means that if you have the Helmholtz potential function or energy function, then if you take the derivative of this with respect to uh, the infinitesimal strain tensor, so you get the stress tensor. Next, we have in case dij is equal to 0 and partial derivative of theta with respect to xi is equal to 0. Then we have this 0, this is also 0, we only have this term. So we have rho, partial derivative of a theta plus rho n whole times d theta dt is equal to 0. So this is varying, it is not equal to 0. Therefore, this is eta, of course. So eta is equal to minus partial derivative of a with respect to theta. So if you have the Helmholtz energy function, if you take its derivative with respect to theta, you can get entropy. So we can measure a, both a and theta, and then we can form a, and when we take the derivative of a with respect to theta, we will be able to find entropy. And then we have the case in case dij is equal to 0 and d theta dt is equal to 0. Yes, so this term and this term are 0, so we have minus qi theta partial derivative of theta then xi. This is supposed to be greater than 0. So it means that if you have let's say if you find your qi and this qi, the heat inflow, it should be it should satisfy this equation. So if you look at for example the Fourier heat conduction law, there it was q was minus kappa del theta. So if we put it into if we plug this into here, so we have the minus 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 becomes plus, so we have minus kappa del theta divided by theta, partial derivative of theta with respect to xi should be greater or equal to 0. So this becomes positive, so it becomes k del theta, theta partial derivative of theta xi. Let's write it this way because we don't know whether it satisfies this equation or not. And then we know that k is already positive for a steady state problem. Therefore, we have k divided by theta, and this is the partial derivative of theta with respect to xi. Then we have the partial derivative of theta with respect to xi, which basically satisfies the equation because this actually is the product of the same, so it becomes squared. Since we don't have we have I in here, so I'm not going to put something like this around it. It's incorrect. So k is positive for a steady state problem and theta is also positive, so therefore this is always positive. So that's why the Fourier heat conduction law can satisfy this equation here. All right, so far we discussed the principal equations in their differential form. However, in the next module, we're going to also provide the integral form of the principal equations. So again, we have the conservation of mass, linear momentum, moment of momentum, entropy inequality and energy equation, but we will basically represent them in their integral form. However, you have to keep in mind that they are referring to the same principle, but in another way.